Take a deep breath. You are likely focused on the oxygen you need, but 78% of the air filling your lungs is nitrogen. Your body ignores it. This gas washes in, makes no contact with the bloodstream, and is pushed back out into the atmosphere with every exhale. These atoms have a violent history. The nitrogen you just inhaled was forged inside ancient stars and scattered across the universe during supernovae. We spend our lives moving through an ocean of stardust that remains undetected by our senses. Though our lungs have no use for it, nitrogen is a requirement for life. It is the building block for DNA, proteins, and the enzymes that regulate cellular function. Atmospheric nitrogen exists as two atoms held by a triple covalent bond. This strong bond makes the molecules so stable it rarely reacts. Because plants cannot break this bond, the airborne gas simply bounces off the organisms that need it. If the atmosphere is chemically inert, a specific process is required to move this stardust from the sky into the soil to build proteins in our bodies. Nature relies on a specific recycling system to overcome this chemical resistance. It takes extreme energy to split a nitrogen molecule. A lightning strike provides enough heat to shatter those bonds, forcing nitrogen to combine with oxygen and fall to the earth as nitrates. In the soil, specialized bacteria perform the same task. They function as biological processors, converting nitrogen gas into ammonia that plants can finally utilize. Once fixed in the soil, plants absorb the nitrogen. It then moves through the food chain as animals consume the plants, and we, in turn, consume them. This natural cycle is slow. For most of history, the limited speed of bacterial fixation served as a biological bottleneck, placing a hard limit on how much food could be grown and how many people the earth could support. In the early 20th century, humans developed a way to bypass this natural limit. The Haber-Bosch process used high pressure and heat to pull nitrogen from the air and transform it into ammonia on an industrial scale. This allowed for the creation of mass-produced synthetic fertilizers. We no longer had to rely on the pace of soil bacteria to replenish our crops. This chart tracks global population alongside synthetic nitrogen. The line remains flat for centuries until this point, where you see a vertical spike in people the planet could sustain. That trend continued, pushing global population toward 8 billion in just over a century. Approximately half of the people alive today depend on this single chemical process for their food supply. We have learned to turn the air into bread. Beyond the farm, we use nitrogen by changing its state. When cooled to -196 degrees Celsius, it becomes liquid nitrogen. At this temperature, biological activity is suspended. This allows for the long-term storage of blood, stem cells, and reproductive tissues without decay. In manufacturing, that same lack of reactivity is used to build electronics. Nitrogen creates the inert environments necessary to prevent oxidation when assembling modern semiconductors. It also powers aerospace technology. High-pressure nitrogen gas is used to clear propellant lines and cool the sensitive systems required for spaceflight. What began as a requirement for cellular life has evolved into a tool for our most advanced industrial and technological systems. Nitrogen does not burn like oxygen or explode like hydrogen. Its power lies in its stability. It functions as both the architect of our genetic code and a primary driver of modern civilization. The gas you are breathing right now, the breath you likely didn't think twice about, is the substance that keeps us alive and propels our technology forward. We focus on the elements that react before our eyes. But the forces that truly sustain our world are the ones we cannot see.